Okay, so today we just finished talking about the progression of like the study of matter from all the way from the Greeks up through the alchemists into kind of the modern scientists, and now we know that there are these things called atoms, and now we will start to wonder, well, what the heck did they look like? So we started coming up with models of the atom, and this is kind of how this goes. And you're going to see that the models of the atom start off kind of weird and pretty basic, but as we learn more information, as we discover more things, the model needs to be changed. And that's kind of the idea of science. It builds on the previous knowledge of the scientists that come before you. So if we're looking at models of the atom, and there's a video here that I will link to in the Brightspace lesson. But by the 1800s, we finally got rid of that four-element theory, and most scientists started to agree that particles are there's a bunch of different elements, and they are made of particles, and they're called atoms. And it took about 2,000 years, but finally Democritus was right, and he was proven right. So along comes one of our first major players in the models of the atom, and his name was John Dalton. And he came up with just a very simple idea of what the atom might look like. And his model basically said that all elements are made of atoms. Atoms are indivisible and indestructible, and that comes from that Greek word atmos or atomos, where it's uncuttable. So you can't break atoms down. They're really hard, and they make up every element. So every element that's on Earth has its own type of atom. And then he also said that atoms of the same element are exactly alike. In other words, they have all the same properties. They look the same, they act the same, they weigh the same. Now, if you take atoms and you put them together, so you take different elements and you put them together, you make a compound or a molecule. And this is basically what we've been saying forever. We still use this model. And in fact, when we draw what an atom looks like really quickly, we often draw Dalton's model of the atom. The other thing is he says that atoms can't be just created or destroyed. You can think of an atom like a Lego brick. If you build one thing out of Lego, you've got some structure that you've built, you take it all apart and you use the same pieces and you put them back together in a different way. You didn't destroy any Lego bricks, so you just put them together in a different way. And that's really what atoms are. They're the Lego bricks of matter. They're the building blocks of matter. And Dalton imagined that they looked something like this. He imagined that they were basically like a billiard ball, like a pool ball. If you went and shot pool at the pool hall, that's what they would look like. But the difference is they are different sizes because they have different masses. So he basically just imagined them all to be solid spheres, solid balls. And honestly, most often when we draw atoms, we just draw little circles. And that's using basically Dalton's model. Now, we understand nowadays that there's a lot more going on in the atom. It's just not this solid thing. There's actually stuff inside that solid thing. So we had to adjust that. So along comes another guy by the name of Joseph John Thomson, or old J.J. Thomson. I like to call him the Muffin Man. This might help you. He didn't live on Drury Lane, but we can call him the Muffin Man, because this might actually help you remember his model. And what he was doing is he was running electricity through a gas, and he discovered this really light, super light particle that had a negative charge, and he called that charge, or that thing, an electron. And basically, he proved that there's parts inside the atom. So it's not just a solid ball, there's stuff in there. So we're actually taking it a little bit deeper. He also later discovered these positive particles called protons. And he imagined that the electrons are super small, they have negative charge, and this atom is like this sphere of positive energy. That's what keeps the electrons around. The negatives and positives attract, because we've heard this before, that opposites attract. And he imagined that the electrons were stuck inside this positive sphere, and that's what kept the atom neutral. So atoms you should have the same number of positives and negatives, keep everything neutral. We need to have the electrons stuck in there somehow. So lots of people from the old days will call this the raisin bun or plum pudding model. I've never really liked raisin buns, and I've never had plum pudding. So another way to think of it is like a blueberry muffin. The cake part of the muffin is the atom, and that cakey part is all cakey and positive, And the blueberries are like the little electrons that are kind of stuck inside. So you imagine, or you can also think of a chocolate chip cookie, whatever you want to think of, but these things are the electrons, and they're stuck inside, and they're all negative, right? They all have this negative charge. They're stuck inside this sphere of positive energy. Now again, it looks like it's a circle. Remember, it's going to be three-dimensional, so it's a sphere. So we've kind of taken Dalton's model and we've refined it. So notice it's still kind of the same idea, it's just now we know there's stuff inside that ball. So along comes a guy by the name of Ernest Rutherford. And Rutherford does a very, very famous experiment. There's actually a picture of Rutherford on the New Zealand $100 note, I guess it would be. And it's actually got some data on there from his famous experiment. His experiment is called the gold foil experiment. And what he did was he actually shot a beam of alpha particles, which at the time they didn't really know what they were, but now we know them to be protons. And he basically shot these alpha particles at a piece of gold foil, a gold leaf, if you will, super thin sheet of gold. And he imagined that the particles or the atoms should be mostly empty space. And that means that most of these particles that he's firing at the foil should just go right through. Imagine shooting a really high-powered gun at a piece of paper towel. The bullet should just go through. But what he did notice was that some of these bullets, these little alpha bullets, the particles that he shot, actually got ricocheted backwards or sideways. And how did he notice this? Well, he had a detector screen around that would light up any time it got hit by a particle, much like an old tube TV would work. And he also noticed that some of these particles actually got pushed off their paths a little bit on an angle like that. So there's something in there that's kind of deflecting these super tiny particles that should be just passing right through. It's like getting an X-ray, but all the X-rays bounce off your body. That shouldn't happen. So, because these particles should be small enough to just pass right through it. So what he imagined is there must be something super dense, super positive stuck inside that nucleus. Stuck inside that atom. And in doing so, he actually discovered the nucleus. So we call his model the nuclear model. And so what he said was that there's a nucleus. And it's kind of like, the nucleus is the center of a cell. Well, the nucleus is the center of an atom now. And the nucleus in an atom is dense, super, super compacted, and positive. And he deduced that from his experiment, that it was actually repelling the little positive particles he was shooting at it. He imagined then if the protons are positive, that's where they must be. They must be in that nucleus. And the nucleus is surrounded by mostly empty space. The negative electrons, we still know there's electrons, so they have to be somewhere. So we imagine that they're kind of like buzzing around the nucleus. They're attracted to it, but they're moving around fast enough that they just kind of almost like in a cloud around the nucleus. It's almost like a bunch of flies buzzing around your head, or mosquitoes buzzing around your head, same idea. So there's lots of space around your head, but the mosquitoes are in there somewhere. They're really small, but they're there. And we call this model the nuclear model. So this is kind of what he imagined it to look like. So the dotted line represents, we can almost think of this as your electron cloud. And the electrons are in there, and they're just zipping around every which way, right? And that's what we've kind of come up with, or what Rutherford had come up with. Now, he's pretty close, but if you think about his model, there's one thing that's kind of doesn't work. And we've just talked about this, that opposite charges attract. So the electrons are going to be attracted to those protons. And that's not good, because now you have electrons crashing into the nucleus, which actually, in essence, could make like a nuclear bomb. They'll just blow up. So we need to fix that. There's something a little bit wrong there. And there's a lot more science behind how the next guy came up with his ideas and what made him think of these ideas. But we have to refine this model a little bit further. So a guy by the name of Niels Bohr basically thought what we were just saying, that the electrons would crash in the nucleus, and there must be something else going on here. So he imagined the planets going around the sun, and every planet is super attracted to the sun. The sun has a ton of gravity, but why don't we actually crash into the sun? Well, because we are traveling through space at a speed fast enough that we maintain our orbit, much like the moon maintains its orbit around us, the satellites that we've put in orbit maintain their orbit around us without crashing into the Earth. So if we have enough speed, enough energy, then we can stay outside of that nucleus without a certain distance without crashing in. So what he imagined was that electrons are moving around the nucleus in these specific energy levels, and he called them orbits, just like planets going around the sun. And he said that every atom in the electron has a specific amount of energy. High orbits, like so if you're far away from the nucleus, that means you have high energy. If you're close to the nucleus, it means you have low energy. It's like if you want to jump off the ground, you've got to push with lots of energy to get higher, to get farther away from the ground. He also said that electrons aren't allowed to exist between orbits. It's like you can't be in grade 6.2. You're either in grade 6 or in grade 7. You can't exist between grades. You are either in one grade or the next. Same thing with electrons. They're either in orbit 1 or orbit 2 or orbit 3. There's specific amounts of energy they're allowed to have, and that's it. He also imagined that every energy level is a specific distance from that nucleus. So the more energy you have, the further away from the nucleus you can be. And he also said that electrons are much more stable at lower energy levels. They'd rather be close to the nucleus. I'm a lot more stable on the ground than I am at a very high height because it's not nice. It's, if you have a fear of heights, you're not very stable at that height. And then the other thing is he said that there's a specific amount of electrons that are allowed to go in every orbit. And for our course, we're only worried about the first 3 energy levels or orbits. So you're allowed to put 2 electrons in the first one, 8 electrons in the second one, and 8 electrons in the third one. And there's some math that goes behind that and reasons why you're only allowed 2, 8, and 8. But for right now, we're just going to know that that's what it is. So we call this model the planetary model. And his model would look something like this. So you've got your 2 electrons in the first orbit, 8 in the second, up to 8 in the second, and then up to 8 in the third. And if we wanted to see the models kind of all together, let's see if this will load up. Oh, apparently we're not allowed to look at that one. So I will show this one in class, the models of the hydrogen atom. But you can also, we can also talk about the next atomic model, which is what you'll get into in grade 12, which is the quantum model. And we've learned a little bit more about the atom and how it's put together. And that comes out with, we take Bohr's model and we take it a little bit more in depth. Bohr's model works really well for simple atoms, but the more complex atoms make it a little bit messy. So let's see if this one would, let's try this one. This is the one I was hoping we would get. So this is what the models would look like. So I'm going to flip to the model. So here's the billiard ball model. And if we shoot light or energy at the atom, things just bounce off. But later on, we started realizing that actually some of that energy gets absorbed. So what J.J. Thomson said, here's his plum pudding model, absorbs certain amounts of energy and the electron just rattles around inside that positive nucleus. Now if we go to Rutherford's model, here's the electron buzzing around, but oh, kaboom, doesn't work. So this is what Bohr's model looks like. And the reason why Bohr figured this out is because if you hit the electron with certain amounts of energy, it jumps, and then it falls back down and releases a specific amount of energy. And you can actually see that when it, if it gets a hit with something here, boom, now it jumped out, and then it fell back, and it released a certain color of light. And we can actually even show those colors of light. I'll speed this up so you can actually see. These are the colors of light and the types of light that the hydrogen atom is actually emitting when that electron's jumping up and down. And then it gets really messy when we start looking into the quantum model of the atom. It's a little bit crazier, but we will get to that in grade 12. But those are the models of the atom, and the main thing that I want you to understand is how the model progressed and that the model of the atom has changed based on the information as we learn it, as we do more and more experiments.